Good afternoon, class. Let's get started. Okay. So I'd like to begin, maybe today if we're lucky, we actually could sort of wrap up our march along the electromagnetic spectrum. So we've been talking about radio waves, microwaves, and we got to the fun stuff that's visible light. Once we get past visible light, we'll talk a little bit about UV today. And there's not a whole lot to say about X-rays and gamma rays other than stay away from them. So they're just really energetic, very tiny, very fast electromagnetic waves. And maybe another reason we won't talk much about them is because it's hard to demonstrate deadly cancer rays in class. So I won't have everyone come up here and get an X-ray. Next time you're at the doctor, just go, hey, that's crazy. You can see inside me without opening me up. That modern medicine is a good thing. So that's about all I'll have to say about X-rays and gamma rays. So anyway, last class, if you remember last class, we were talking, I ran up to the back of the class and I was playing with these polarizers and making funny colors on the projector. And that's right about the time people's brains start going, hey, wait, we need a review for the midterm. So really quick, just to review the way last class ended. I had these things called polarizers, and it's worth just reviewing what the heck that is. And what a polarizer is just a filter for light, for electromagnetic waves. And the way a polarizer works is it takes advantage of the fact that light waves are indeed moving up and down, or side to side, or at least some way transverse to their velocity. So when I shoot a laser at you or a flashlight at you, anything like that, even a radio at you, that light beam, that photon is moving in a straight line. But what a straight line photon consists of is two orthogonal waves of the electric field and magnetic field. And so as my beam is going this way, I might have an electric field doing this. And so I can make this filter that is chemically designed to absorb the waves going in one particular direction, but then to let pass waves going in another direction. So one of the main points we've gotten out of the last couple weeks is that there's a whole bunch of things called photons, a whole bunch of different things like microwaves and radio and all that we associate with photons. And one of the things that changes when I change a photon's wavelength and frequency is how it interacts with matter. So that's a really important thing that we've been talking about, is how photons interact with matter. How a photon interacts with matter depends on its wavelength and frequency. And so I've got visible light. Let's talk about that. Visible light, let's talk about red, green through purple. Visible light is photons of a pretty narrow spectrum, like 400 to 700 nanometers in wavelength. Those types of photons will bounce off of things like walls and ceilings and me and you. You and I don't transmit visible light very well, otherwise we'd be transparent. So the term transparent and opaque usually is just humans saying transparent and opaque to this thing I call visible light. But I think just about everything is transparent or opaque to some type of photon. So you might be opaque to visible light, but a radio wave or a microwave goes right through you, and vice versa. So this filter I have is particularly designed that it's transparent to light going one way, but it's opaque to light going a different way. So a couple reasons I even brought that up last class. One, just to remind us that light is a transverse wave and it goes up and down, and that I can take advantage of that to filter out light. You might have heard of like polarized sunglasses. I think my ski goggles are polarized, and I think this is not just a sales gimmick. I think when light reflects off of snow or off of water, it's polarized mostly in one direction. So if you want to eliminate glare but still be able to see the stuff in front of you, you can polarize your sunglasses in a particular direction. I think that's not just a sales gimmick. It seems to work. Another reason I brought it up last class is in a class called How Things Work. It's nice to know how some things work. Here's how the projector in the back of the room works. It's got a bulb in it. You can see my light source down there. It's got a bulb in it. It's one of those old-fashioned bulbs. Here's how it makes light. It just gets crazy hot. And if you've ever looked into a projector, you shouldn't. They are crazy bright. They are very, very bright. And so the projectors are usually making, I can hear this fan up here right now. Projectors usually have loud fans attached to them. I'm going to leave, I think that one's probably fine to turn off. Projectors usually have loud fans attached to them. If you ever turned off a projector, usually you'll hear the fan go for another minute because the bulb inside a projector gets about the surface of about the temperature of the surface of the sun. We're talking like 5,000 to 6,000 degrees. That's why it's so nice and bright white. So if I want to make a nice bright light that's going to shoot all the way from the back of Physics 203 to the front of Physics 203 while the rest of the light's on and still be able to make an image and still be able to convince you that's white and that's black to make enough contrast for your brain to think there are two different things even though they're both white, that's got to be pretty bright. So I've got this thing that's like the temperature of the sun. But then this thing is plugged into a computer and I need to be able to make images. I need to be able to make cool graphics like that. In order to do that, I have to be able to separate out the red, green, and blue. And the reason I only need to do those three things is because I'm assuming a human is going to be looking at this projector. So things like the screen on your phone, the screen on your laptop, and the projector in the back, those are things made to be looked at by humans. And we know that humans are only receptive to three types of light, red, green, and blue. Those are the primary colors of primary additive colors, the primary colors of light, RGB. And so if I want to make all the colors that a human will ever perceive, all I need is just three colors. I need red, green, and blue, and then with some combination of that, I can convince a human that I'm making magenta, I'm making gray, I'm making purple, whatever else I'm making, just with those three colors. So here's what goes on in the projector. I've got this super bright light. That super bright light goes through a mirror. One of the things I've mentioned, it's come up at least once in this class. A mirror is a clever device. It's usually a piece of glass coated with something like silver, and the light bounces off that silver. So we know silver is a metal, and metals are reflective. And if I polish it really good, I can reproduce the image. I can bounce light off. Well, scientists have gotten pretty good at making mirrors, and we can actually do selective mirrors that let most light bounce off. But as we've talked about, how light interacts with matter is frequency dependent. So I can make a mirror that lets red and green bounce off, but lets blue pass through. That reflects red and green and lets blue pass through. And on that mirror right there, on that first picture, you can see that red and green are reflected off that bottom left mirror. And green and blue, the shorter wavelengths, green and blue, the shorter wavelengths are transmitted or reflected, and red passes right through. Red is the longest wavelength. So somehow I've chemically altered this mirror such that the longest wavelengths, red, pass right through. The shorter ones, green and blue, are reflected. So what I've done is I've selected out red right there. Then the next mirror, I can select out the next shorter set of wavelengths, that's green, and I can let blue pass through. And then I've taken my bulb and I've selected out my RGB. So I've very carefully, just with with mirrors, I've selected out RGB. And then I'm going to recombine those into an image. So what comes out of the projector is going to be some amount of that red that got filtered out, some amount of the green, and some amount of the blue. And that's it. I can filter out everything else other than what I know humans are going to respond to. I don't need to shine yellow photons out of there. We don't respond well to yellow photons. So I can recreate a picture very well with just RGB. Then what I can do, and this is where the polarization comes in, I can polarize the light. And that helps me set up my filter. So rather than just having all three colors streaming out all the time, I somehow need to arrange, I need to decide what part of, where in this picture do I let the yellow through, and where do I let the green through, and where do I let the blue through. And it's pretty amazing that this picture right here is 1024 by 768. So do that math, how many pixels that is, 1024 by 768, that's something like close to 1 million. There's about 1 million pixels up there. Each pixel is subdivided into RGB, so that's about 3 million dots up there. So that projector in the back is deciding at 3 million places, do I let the green through? Do I let the blue through? How much? And there's these little LCD, these little liquid crystal displays. It's kind of like your TI-83 or your any calculator you've probably ever used has a liquid crystal display. That liquid crystal display can transmit or block polarized light. So because I take advantage of the polarized light and I have an LCD in there, I can turn on and off these pixels and make colors change. So I could play a movie. I could play a movie on one of those projectors. I don't have a movie loaded up right now, but if I were to play a movie, you'd be watching 3 million dots change at around 30 times a second. That's pretty impressive. So inside that projector, I've got 3 million dots that are deciding what light to let through, and they're deciding 30 times a second and changing. And we humans think that's a movie. But what we're really seeing is just 3 million dots changing their intensity 30 times a second. It's a pretty impressive feat for that to be able to happen. Okay. So where we're going to kind of go for the next little bit today is a few more examples of things that humans perceive and really what's actually going on. And I think a good place to start is similar to the projector. So a projector is just a source of RGB, and then you and I perceiving that. And yeah, there's our sensitivity, just RGB. I think I want to spend a minute today, before we go any further, I want to spend a minute talking about how you and I perceive these other colors that aren't RGB. And that might be a good time to do the eye clicker. Yeah, let's do an eye clicker now. Yeah. Okay, so here's my eye clicker question for the day. I have a, not now, well, it's sort of magenta, and so, no, not really. Say I had a magenta shirt and a cyan tie. Cyan is that kind of tealy blue-green that you're seeing up there. I have a cyan tie and a magenta shirt. I'm going to shine just blue light on that outfit. If I were to shine just blue light on that outfit, what would I see? So A, the shirt would appear blue, and the tie would appear black, or black and blue, or blue, or red-green. Okay, let's take 15 more seconds. I like this even distribution we're getting here. That's nice. Not sure what's going on there. Okay, let's lock in your answers. Okay. Let's give it a shot. So up there on the top right, I actually have a magenta shirt, and right now it's illuminated with no light. So most of the things you deal with on an everyday basis do not emit light on their own. The moon does not emit light, it just reflects sunlight. You and I do not emit visible light, I should say. Everything emits invisible light. You and I, if all the lights were to go out in this room, we couldn't see each other unless you had sensitivity to infrared. So most things do not emit light, including my magenta shirt and cyan tie. I have to illuminate them with something in order to get something back. So my magenta shirt has some dyes in it that reflect a pattern of colors or a series of colors that you and I are going to perceive as magenta. Magenta is actually a nice mix. You can actually see it here. You can see it here. Magenta is this nice mix of blue and red. So that's magenta. By the way, as I'm reorganizing the circles on the screen, I want you to realize that what you're seeing right now is coming out of the projector, and the projector only makes red, green, and blue. So right now, what you're seeing in this region right here that looks like magenta, what's happening is the projector is just putting lots of red next to lots of blue. But there's no magenta coming out of the projector back there. In fact, there's no white coming out of the projector back there. Right now, what's happening in that area your brain is telling you is white, is the projector is shooting red right next to green, right next to blue, but they're so close together, your eye thinks they're coming from the same spot, and your eye thinks it's white. There's only 3 colors coming from the back of the projector in the back of the room, and white's not one of them. So right now, they're only making red, green, and blue. If it puts red and blue right next to each other, you're going to perceive that as magenta. So that's what you could pretend, you can assume that magenta light is being shown right there. The question was what, about blue light, right? So if I take blue light and put it on my shirt, magenta reflects blue and red. If I shine blue light on a magenta shirt, that shirt's ability to reflect blue, it's going to do it. It's going to exhibit that behavior. There's no red incident upon the shirt, so there's no red for the shirt to reflect, so you're just going to see a blue shirt. Cyan is blue and green, so there's my cyan. So my tie, it reflects blue and green. And if I shine only blue on the tie, actually I just gave away both of them by putting the blue on. There it is. There's the blue, blue shirt, blue tie. So you're not even going to be able to distinguish. Now this would be a pretty remarkable outfit that was so just reflect blue, 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 and you couldn't even distinguish the two. But that's what it would look like in an ideal world. So in order to get cyan, I need to put some green on there. That's not going to change the shirt, because the shirt reflects red and blue. And if I were to put some red on there, you get to see my magenta shirt, but the tie needs green, so I need to put all 3 in order for you to see my outfit. Okay? Hopefully that makes sense. So it's worth knowing that the primary colors of light are RGB, and you can see the combos up there. So this is different than your art teacher told you probably, because the art was usually dealing with paints and pigments. Pigments are subtractive. If I want to make yellow's not a primary color. I need to shine red and green into your eyeball. And it's weird to think red and green make yellow. I don't know what color is, but if I'm dealing with what human brains tend to perceive, if I send red photons and green photons, your brain's going to say, hey, that's yellow. And that's what's happening right now. The projector, I promise, doesn't make yellow. The projector is shining green and red right there, and your brain is saying, hey, I'm going to call that yellow. Okay. Any questions? Yeah. What about pink? Great question. If I shine just red, go back to my, if I shine just red at you, like a lot of red, your eye is going to perceive this nice, bright cherry red. That's like a color that humans are sensitive to. And then if I send in equal measures of blue and green on top of that, your eye is going to start to see whitish red or pink. And so if I shine equal measure of red, green, and blue, now if I had really made my little animation sweet, I could have tweaked all 3 of those values, and I could have made other colors. But right now you're seeing full-on red, full-on green, full-on blue, and that's all I have up there. But you can imagine if I just said all red, green, all red, green, and blue, you'd see white, and I could like sort of tone down the blue and the green, and you'd get reddish white, which you would interpret as pink. Yeah, good question. I want to try a little experiment real quick. Let's see if this works. Here's my experiment. I don't know how well this is going to work, but we're going to try it. I'm going to see if I can turn off the lights in the room, including the side projector. So right now, pretty much the main source of light, I guess other than like 80 laptops, the main source of light in this room is that white light. And so if you were to look around the room, everything's darker because there's less light, but probably pretty true to the color it was a second ago. So the fluorescent tubes in the ceiling were making white light, which is a combination of all of them. My projector's not making white light, it's just making red, green, and blue, but that's pretty close. And so if you look around the room, your shirt's about the same color it was a minute ago, your skin is about the same color as it was a minute ago. I don't know how well this will work in a room this size, but if I ask the projector to just make red light, you'll see that let's see, if you were, a minute ago were reflecting any red light, you're still reflecting that red light. If you had a red shirt, that red shirt still looks red. But things that have no red in them just go kind of dead. And so if you had a yellow, if you had a purple shirt, right? No, green and blue. Yeah, if you had like a teal. If you're wearing like anything kind of tealish, that'll just kind of go out. It'll kind of go gray. I'm trying to remove most of the blue and green in the room by doing that. So if you watch, teal colors really kind of turn on and off a little bit when I do that, as opposed to your reds just kind of stay red. And then if I go green, anything purpley will kind of go out. And so you'll see around the room, you'll just see like different, like if you're looking in front of you, the shirts of the people in front of you, some of those will change colors, some of them kind of won't, based on what colors are in them. Let's see, blue, any yellows are going to kind of go away. And then let's do cyan. Let's see. One of the tricks sometimes, like I think movie producers use, is I can right now this is cyan, so this is green and blue. I've taken the red out of the light, and so right now, if your skin tone tends to reflect any red, you'll look a little more corpsey in this kind of light. So we've removed some of the red. Depends on your skin tone, but sometimes that's a way to make things look a little dead. And then this is magenta, so this is green and blue, or this is red and blue, so I've taken away the green. Okay. So anyway, as I flip through the colors, you can just kind of see things in the room. You can see things in the room, like that Tide box in the front. That Tide box in the front, you can see kind of changes colors based on what I'm shining in the room. But anyway, that's only a little bit effective when there's so many other sources of light in the room. Okay. I'm going to turn the lights back on for just a minute. I think that's really bright. Okay. Let's see. I think what I'd like to do today is look at a couple other examples of how humans perceive light and some of the ways that gets tweaked. And then maybe toward the end we'll do talk a little bit about X-rays and gamma rays and UV light. Okay. Let's start with this one. Yeah. Oops. Let me turn the lights back down a little bit. That should be okay. Okay. I think we'll start with I think a lot of humans is one of their favorite representations of how light can be tweaked, and that's a rainbow. I think everyone loves a rainbow. I think it's worth noting that I think not that long ago, Newton's time, people looked up in the sky and saw a rainbow. I mean, obviously in biblical times we looked in the sky and had very different ideas of what that meant. But then even in Newton's time, we looked up in the sky and saw rainbows and were confused by that. Now, white light is kind of what our sun gives us. So it's I think it's forgivable to think that white light is the purest light, that white is some sort of purity in that. And then anything other than white light is a distortion or a tainting of that, right? I think that I could see where people would come up with that, but that's crazy. And really, when people saw that, people assumed, okay, so what I'm doing right now is I'm shining white light through a prism. And when I shine white light through a prism, it comes out in crazy colors. And it's very easy to assume what's happening is there are probably impurities in that glass, in that crystal, that are tainting or distorting the light. And so what's coming out is some colored version of the light. And that's actually the opposite of what's happening. What you're seeing is the true colors. White is just the combination. And yes, all of the words coming out of my mouth have these racial overtones. I recognize that. So we can forget that right now. So we're just, I'm seeing people going, he said white. So we can forget that for a minute. We're just talking about photons. So anyway, so really what's going on here is white is just the combination. White is just the combination of all the different colors that you and I are perceiving. So you and I perceive red, green, blue, and we say, hey, that's white. Then what's happening is those are just being separated. And so one of the things I've said over and over this last few classes is that how light interacts with matter is frequency dependent. One of the details I probably haven't said yet is that when light bends in a medium, and maybe we should talk about that a little bit. Yeah, we'll talk about that a little bit. When light bends, and it does, in a medium, the amount of bending is almost always dependent, almost always increases with shorter wavelengths. So red almost always bends less than purple. So when I shine light through a prism, it's going to bend. And the reason it's going to bend is it's gone from one medium into another. So as light goes from one medium into another, it's always going to bend. And the red light is going to bend less. And then the orange light's going to bend a little more, the yellow's going to bend a little more than that, and the purple's going to bend the most. And so what you're seeing is white light being dispersed. The term for that is dispersion. So maybe that's a good word to know. The term for that is dispersion. And the reason it's being dispersed because of the different frequencies, the different wavelengths. So red, and you can even see it. Notice the light wants to go straight. Some of it is. There's a little beam of light over there. The light wants to go straight. The red took a slight left turn and ended up over there. The orange took a slightly bigger left turn and ended up just to the left. The yellow to the left of that, and then the green, and then the blue, and the purple. So you can see that all of the light got bent to the left. It was going that way. It got bent to the left, but the higher the frequency, the more the bending. The higher the frequency or the shorter the wavelength, the more the bending. Caitlin. Good question. Caitlin asked, what are we seeing up here? Right now, the source of light is a bulb that's super hot. So coming out of that bulb isn't just red, green, and blue. So coming out of my projector in the back is only red, green, and blue. But coming out of that is all of them. So the whole rainbow is coming out of this light bulb. But where you see yellow, for example, actual yellow photons, I'll call them yellow just because they have a wavelength of around 550. An actual yellow photon is hitting you in the eye. That's where the RGB difference happens. A yellow photon hits you in the eye, your red and green receptors will get fired off in equal amounts, and your brain will say, hey, that was a yellow one. And so what's happening is from a certain region on that screen, there's actual yellow photons, actual 550 photons. It's not just red, green, blue up there, it's the whole rainbow. But then your eyeball only has 3 types of receivers, and so when I fire off your green and your blue, your green and your red equally, your brain goes, okay, well, that must be yellow. So your brain is correctly, I guess, perceiving, oh, that's not, that's 550. And the reason I know it's 550 is because my green and reds are going off equally. Good question. Okay. So there's your simplest way to make a rainbow. And so like I said, back in Newton's times, a lot of those guys thought, okay, what's happening is this crystal is distorting or tainting the light, and that's why it's a different color. But really, it's just being dispersed into its particular frequencies. So white is just all of them together, and normally you don't get to see them nice and spread out, nice and dispersed, but there you can do that. Okay. Another example of people thinking that the light is being tainted or diminished in some way. One of my favorite YouTube videos I saw a while ago was somebody, I think they were in California, and they're out watering their grass. And hopefully everyone has seen this. When you water the grass, you're at or if you ever other type of mist, you'll see a rainbow. And this person was filming it and putting it on YouTube for the reason to let us all know that the government is messing with our waters, because the rainbow is evidence that our water's been screwed with, because it's making that rainbow color. And you know that there's something wrong with the water when it makes a rainbow. And they go on for 5 minutes about this great conspiracy theory they have. Not true. rainbows are just the same thing we're seeing up here, except with water droplets. And let's see, I've got a slide for that. There it is. So let's talk a little bit about rainbows today. I've got time for that. And so this is one of those classes, I've said this a few times this year, that I hope you walk out of this class and, then a year from now you're at a party and something about the physical world comes up and someone will turn to you and go, you went to UVA, you probably know the answer. How do rainbows work? And you'll say, yes, I went to UVA, and just because my guidance counselor in high school said you're not a science person doesn't mean I don't get science and I am familiar with certain scientific concepts, and I'm a scientifically literate person because I went to UVA. And so a scientifically literate person knows how rainbows work, and here's how rainbows work. I am standing outside and the sun is up and the sun is passing over my head. The sun is behind me. The sunlight is passing over my head. And then it's encountering something very similar to what we're seeing up here. It's encountering something that is causing the light to bend. That's called a refraction, by the way. So the light is bending just like it's doing here. Now, in the front of the room right now, this projector is bending light, I don't know, it's bending light like 30 degrees or something like that. So when light passes from one medium to another, it'll bend. That's called refraction. That's happening about 30 degrees up here. That can happen a much steeper angle, and it can happen in a water droplet. So you're seeing a picture of that up there. The visible light is coming over my head, and in front of me, because it just rained, there's lots of spherical drops of water floating in the sky. There's water droplets all in the nice humid sky right after a rainstorm. And those water droplets are all over. They're not just in a bow. They're just in front of me. That's all there is, just a bunch of water droplets. As the light goes over my head, it's going to enter each one of those water droplets, and the light's going to get refracted. And you can see it actually reflects off the back surface of the drop and then refracts on its way out. Both of those events, the reflection and the refraction, are frequency dependent. And so the purple's going to do it the most, blue a little less than that, green a little less than that, and then red the least. And so what I'm going to get is I'm going to get a pattern of reflection and refraction that's going to come back to my eye. And if I look at a particular drop, if I look up in the sky, that particular drop will send light back to me. But it has to be in a very specific angle. And so the light goes over my head and bounces, and if that angle between the light beam and my eye is about 42 degrees, I'll get some of it back. Most of it's going to go back over my head or hit me in the chin or hit me in the chest. Only the part that's going to make it through this tiny 1/8 hole in my head is a very specific angle, and it's even more specific than that. The raindrop just above and just below the one that I'm seeing, maybe yellow is in the middle, the one that's being bent a little bit more, I'm going to see purple, and the one that's bent a little bit less, I'm going to see red. And so there's this circle of raindrops in front of me that constitute all of the drops. So again, the whole sky is full of drops. But there's just this narrow band of drops in front of me that make that angle work, where it's about 42 degrees if I'm dealing with normal air and normal water, about a 42-degree angle that I'll get the raindrops back. So really, you can think of the whole sky as making rainbows, but for every unique observer, there's a unique set of raindrops. And there's that one, that one, that one, that one, and they make a circle that will send light right back into my eye. So some of them are going to go over my head, some of them are going to hit me in the chest. I'm going to get this little band of raindrops that are going to hit me in the eye. And so as I move around, I'm actually seeing different raindrops. That's why I'll never get to the end of the rainbow, because the rainbow is a set of raindrops that are equidistant from my eyeball. My eyeball is the center of a circle, and as I try to chase down the end of the rainbow, that circle is still always centered on my eyeball. And worth noting, it's a circle. And so really, you can imagine a whole circle of raindrops that my eyeball is in the center of. It's just the horizon cuts it off, and it looks like a bow. Some friends of mine and I, a few years ago, sent a GoPro up on a weather balloon just for fun. And as that GoPro was pointed down, we actually caught a rainbow. We caught the whole circle of the rainbow, because the GoPro was at the center of a circle, and then because it was up in the sky, it wasn't cut off by the horizon. We actually saw a whole circle of a rainbow. Totally on accident. It was pretty cool, though. So that's what a rainbow is. It's just light coming back to you. It's It's a circle, but it's cut off by the horizon. Question? Good question. I have a slide for that, I think. Yep. Wait. Yes. No. I hope so. Let me look. Yes, I have a slide. Let's put that one next. If you haven't seen it, go to YouTube. Everyone watch the double rainbow guy. Yes, everyone hopefully has seen the double. If you haven't seen it, go to YouTube, watch the double rainbow guy. There's a guy who gets his mind totally blown by a double rainbow. Here's what's happening is on the far right, you can see the primary rainbow. That's one reflection, one refraction. Sometimes if the angle is actually steep enough, if the angle is steep enough, you can get the light's coming into the bottom of that the bottom of that drop, the bottom of that sphere. It's getting actually reflected twice and then getting sent back out. And so if I'm standing outside, there is a unique set of raindrops that constitute a circle that are 42 degrees from the sun to my eyeball. There's a second unique set of raindrops that constitute whatever angle that is, I forget. And so really, if you think about it, you put your eye in the center of a circle. There's one set of raindrops that are allowing light to go over your head and get bounced back. That's one unique set of raindrops. And there's a second unique set of raindrops that are allowing that double reflection to happen. So most raindrops are allowing both of those to happen, but you just have to be standing in the right spot to perceive, or not, you don't have to be standing in the right spot. Yeah, the conditions have to be right for you to be able to perceive both those. So it has to be dark enough outside that you're not getting all these other photons. But it's just two reflections inside the raindrop, and that changes the angle. And you'll see, 40, I wish the other one had the angles on it. But you'll also notice on the primary rainbow, the red's on the bottom. On the secondary rainbow, the red's on top. And so if you ever see a double rainbow, they're flipped. So it'll go Roy G. Biv and then Biv G. Roy or whatever. It'll flip around. Okay. Let's do one other example. While we're talking about sky and stuff, 6 minutes left. I think we have time to do this. Yeah, let's do this one. Again, you're at a party. People are like, okay, you went to UVA. Tell me how sunsets work. Six minutes left. This should work. Right now you're seeing the sun, right? The sun sends out equal portions of red, green, and blue. And that's our sun. Looks a little bit more like the moon. But anyway, it's a equal portion of red, green, and blue. And usually when I'm on Earth, I'm not just getting the whole sun directly pointed at me. I'm usually having to deal with the fact that there's an atmosphere between me and my sun. So when I look straight up at the sun, at high noon, I'm going to see a pretty white sun. It's slightly yellow because a lot of the blue's been scattered out. Hopefully this will start, if you look at the tank itself, it'll start to look a little bluish as this happens. So right now what's happening is I'm trying to replicate the sky. I'm trying to replicate the Earth's atmosphere. So at high noon, like a beautiful day like today, go outside. Sky's blue. We'll talk about that one also in a minute. That's good for parties also. But we'll go out. You'll see the sky's blue. And if you were to look straight up, you're going to see the sun will be yellowish just because some of that blue light's been scattered out, but it's mostly white. But then as the sun sets, the sunlight has to pass through more and more of the atmosphere. And as the sun passes through more and more of the atmosphere, should be getting a little bluer. Hopefully that's getting a little redder, and that's looking maybe a little bit more like a sunset. So as the sun puts out the whole spectrum, the sun puts out red, green, blue, yellow, the whole spectrum. If I were to go on top of the atmosphere, like out in space, the sun's going to look white, white, white. At noon, if I look up at the sky, it's going to look slightly yellow because our atmosphere is going to take some of the blue out. The blue is just the one far end of the spectrum there. Now, there's a chemical reaction happening in here that's slowly making more and more particles that are representing the sun, or representing the atmosphere. And so the atmosphere is going to scatter out more and more of the blue. So where's my spectrum here? So if right now in that bottom picture, you can see the purple and the blue are on the far right. as I remove the more and more of the blue and purple, in other words, scatter it out due to particles or gas in the atmosphere, as I remove more and more, I'm going to get more and more of a nice sunset look because I'm getting just the left end of that spectrum right there. So as more and more is removed, I'm getting a redder and redder tinge. And you'll notice, if you can see that the water up here, the water is turning blue because the water is scattering that half and it's transmitting the other half. And next class we'll talk a little more detail what I mean by scattering, but it's just there's particles in there. There's particles in there that are actually absorbing and reflecting out that component, and that's just this is what I'm left with. So right now I'm left with a nice dark red, and that's probably enough to demonstrate that. Okay. Let's see. Any questions? Yes. Oh, what? Blood moon. Oh, whoa. For a second I was like, what's happening? My stick's in there. So the question's about like a red moon. And so again, the moon is just reflecting the sunlight. There's nothing between the sun and the moon, so it's not like anything on the way from the sun to the moon turned red, but something between the moon and you turned red. And again, I have another picture for that. Let me pull that one up. This is a little bit of a demonstration of that. If you can see at the bottom, I'm getting blue light reflected, but on the top, because the light has to pass through more atmosphere, I'm getting green and blue reflected. I'm just left with red. Still have 2 minutes left. And so anything that causes more of the atmosphere to be reflected out is going to shift everything to the red. And so when I'm looking at the moon, it's usually nice and white because I'm getting this white light from the sun straight at me, especially when it's high. As it goes lower, similar situation. And there's lots of things that can filter out light. One is just more atmosphere. So the atmosphere, regardless of the conditions, regardless of pollution, regardless of anything, there's going to be oxygen and nitrogen that the stuff has to pass through. Oxygen and nitrogen will disperse blue light, and I'll be left with red. And then other things like pollution or smog or soot from a volcano or something. There's other things that can scatter out the blue. But anything that causes it to shift, I mean, look at it now. I'm only left with the darkest red on that circle right now. And so anything that causes it to shift. All right, we'll do more of that next class.